Hi, this is Module 6, Multilayer Neural Networks. In Module 5, we have studied the perceptron in particular, where we saw that it is just either one neuron or a layer of neurons, and it could not solve complicated problems or nonlinear problems such as the XOR problem. Here we'll be looking at a structure called the multilayer perceptrons. So multilayer neural networks are feed-forward artificial neural network models, which are also referred to as multilayer perceptrons. So the addition of a hidden layer of neurons in the perceptron allows the solution of nonlinear problems such as the XOR and many practical applications using the backpropagation algorithm. However, the difficulty of adaptation of weights between the hidden and output layers of the multilayer perceptrons have dampened such architecture during the 60s. With the discovery of the backpropagation algorithm by Rammelhart, Winton, and Williams in 1985, the adaptation of weights in the lower layers of multilayer neural networks are now possible. The researchers proposed the use of semilinear neurons with differentiable activation functions in the hidden neurons referred to as logistic activation functions or sigmoids, which allows the possibility of such adaptation. So previously in Module 5, you have looked at two activation functions or two types of activation functions, namely the binary activation function and the bipolar activation function. So if you remember, binary activation functions gives out only two outputs, it's either 0 or 1, whereas the bipolar activation function gives out three possible outputs, -1, 0, or 1. And as we will see later, the logistic activation functions would give out infinitely many outputs between 0 and 1. And there are also other activation functions available or used in artificial neural networks. So a multi-layer neural network with one layer of hidden neurons is shown below. This is also called a two-layer network. It's called two-layer because it has a hidden layer and an output layer. So for some reasons, this is not considered as a layer. So these are inputs x1 and x2, and we have an output y01. So in this particular structure, we have two inputs x1 and x2 and one output. So the superscript O here refers to output, and the superscript H here refers to hidden. So these are input neurons, these are hidden neurons, and this is output neuron. So depending on the application, we have to select the number of neurons and the number of layers. So if you have, so the input neurons and the output neurons are pretty straightforward to be determined from your data. So if you have three inputs, then you would have three input neurons, and if you have two outputs, then you would have two output neurons. The number of hidden neurons is a bit tricky. We don't really know which would be effective, therefore we have to rely on the trial and error approach to determine the suitable number of hidden neurons. This is a three-layer artificial neural network with two layers of hidden neurons. This is hidden layer 1, hidden layer 2, and this is output layer. So therefore, this is a three-layer artificial neural network. And then again, we have two inputs and one output in this particular model. And as you can see, we have three hidden neurons in each hidden layer. So between each connection we would have a weight. So in this particular model, as you can see, each neuron in one layer is fully connected to every neuron in the following layer. For example, this neuron is fully connected to hidden neuron 1, hidden neuron 2, and hidden neuron 3. Similarly, each neuron in the hidden layer is fully connected to every neuron in the output layer. It doesn't have to be this way, but this particular model is called fully connected artificial neural network. So between each neuron which are connected, we have weights. So all the weights here is called the hidden weight. All the weights here is called the output weight. And we have another type of weight which we will refer to as bias. It's exactly as a weight, but the input is always 1. So this is BH1 because this is J equals to 1, hidden neuron 1. This is hidden neuron J equals to 2, therefore hidden neuron 2. This is hidden neuron 3. This is input neuron I equals to 1. So this is input neuron 1, input neuron 2. And this is output neuron K, where K equals to 1. So this is output neuron 1. So we would assign the name or the symbol of the weight according to the neurons it is connected to. So for example, the weight between hidden neuron 1 and input neuron 1 we will refer to as WH11 JI. This is J equals to 1, I equals to 1, therefore WHJI. And the weight between hidden neuron 2 and input neuron 1 we will refer to as WH21. Similarly, this weight we will refer to as WH22. And the weight here we will refer to as WO11. This is WO12. This is WO13, and so on. And the bias here is called the BO1 because it's connected to neuron K, where K equals to 1. So inside each neuron we would have activation functions. We would see the role of activation functions later on. So this activation function is called the linear activation function, where the output here is exactly the same as the input. So as you can see, you would have infinitely many values of output each time, ranging from minus infinity to positive infinity. And this type of activation function is called the logistic activation function, or sigmoid, where you would have infinitely many output between 0 and 1. So you cannot have anything below 0 or greater than 1, but you can have infinitely many values at once. So let's look at the logistic activation function. Activation functions play an important role in many artificial neural networks. In the early years, their role is mainly to fire or unfire the neuron. In new neural network paradigms, the activation functions are more sophisticatedly used. Many activation functions used in artificial neural networks nowadays produce a continuous rather than discrete value. One of the most popular activation functions used is the logistic activation function, or more popularly referred to as the sigmoid function. This function is semi-linear in characteristic, or we would say non-linear. It is differentiable because it is smooth and continuous, and produces a value between 0 and 1. So this is not like the binary activation function where you would have only two possible outputs, either 0 or 1. Here the possibility is infinite, but it's always between 0 and 1. So I hope you know the difference. So this is the mathematical expression of formula of the logistic activation function. This is the output. We call this hidden output, where YHJ is the output of hidden neuron J. So let's see, where is the output of hidden neuron J? So if we refer to this model, so here is the output of hidden neuron J. So remember, this is J equals to 1, J equals to 2, J equals to 3. So whatever comes out here is YH1, this is YH2, and this is YH3. And this is a function of SHJ. What is SHJ? It's the total of inputs to hidden neuron J. So this is what SH1, SH2, and this is SH3. The summation of signals or values that enter the hidden neurons. So as you can see, the total sum of input to hidden neuron is 1 multiplied BHJ, or if we refer to the hidden neuron 1, it will be 1 multiplied BH1 plus X1 multiplied WH11 plus X2 multiplied WH12. In general, this is the equation of SHJ. So capital I is the number of inputs. So here capital I is 2. We will see later that the total number of hidden neurons we will refer to as capital J. Capital J here is 3. And the total number of output neurons we will refer to as capital K. And the capital K here is 1. So Xi is input I, WHJI is the weight between hidden neuron J and input neuron I. And BHJ is the bias connected to hidden neuron J. The parameter C controls the firing angle of the logistic activation function. So this is the logistic activation function, and you have to memorize this equation and this, of course. So when C is large, remember this is C, sometimes it's called the firing angle. The logistic activation function becomes like a threshold function or the binary activation function. When C is small, the logistic activation function becomes more like a straight line. So let's see the next slide. So when C is low, it becomes a straight line. When C is high, it becomes like a binary activation function with threshold value 0. When C is large, learning is much faster, but a lot of information is lost. However, when C is small, learning is slow, but information is retained. Because this information is differentiable, it enables the backpropagation algorithm to adapt the lower layers of weights in a multi-layer neural network. So let's see the introduction of the backpropagation algorithm. First of all, we have weights, like I said earlier, between the connected neurons, and we have biases. And we have to find the suitable values of these weights and biases so that your neural network model will be able to learn the data. So essentially, in artificial neural network, it is a machine learning tool. So you would give inputs and the ANN model should give you the desired output as in your data. So in order for the network to give you the correct or desired output, these weights have to be selected accordingly. And how do you select the weights? There are many of them, and it's difficult to do to, to, to adjust the weights and the biases by using the trial and error approach. So you need an algorithm. So in perceptron, you saw an algorithm, the perceptron learning rule. And in multi-layer perceptron or multi-layer neural network like this, the algorithm is called the backpropagation algorithm. At least is the basic or the foundation of all the algorithms that we have now. The backpropagation algorithm is perhaps the most popular and widely used neural paradigm. The BP algorithm is based on the generalized delta rule, which in turn based on the gradient descent approach proposed by the PDP research group in 1985 headed by Dave Ramelhart, who was based at Stanford University, California, USA. The backpropagation algorithm overcame the limitations of the perceptron algorithm because perceptrons could not solve non-linearly separable problems or complicated problems. It can only solve linearly separable problems. Among the first applications of the backpropagation algorithm is speech synthesis called NetTalk, developed by Terence Sainowski. The backpropagation algorithm created sensation when a large number of researchers used it for many applications and reported its successful results in many technical conferences. Training of artificial neural network. The algorithm is used to train an artificial neural network as a supervised machine learning tool. Thus, training data is required. And as you know, machine learning refers to a set of tools to understand your data, either to predict or to infer. And it can be categorized into supervised machine learning tools and unsupervised machine learning tools. Neural network in particular is a supervised machine learning tool. As the output of artificial neural network is numerical, why it's numerical? Because let's refer to the first figure. The output is always a number. You cannot have a class or an alphabet as an output here. So if you want to solve a classification problem, you have to encode your classes, which is the output, to numerical values. So for example, if you have three possible values of output classes A, B, C, you may encode the outputs to be 001 for A, and B becomes 010, and C becomes 100 if you want to use the artificial neural network. And if you want to use a decision tree, for example, you don't have to do the encoding because the output of a decision tree model will be classes directly. So that's why it says here, if the output, because the output is numerical for artificial neural network, your target data or the output or the desired output has to be in a suitable numerical form. So examples of training data are samples of handwritten characters, images with given categories, credit card default record, etc. Similar to other machine learning models, the training is done offline, and the training objective is to minimize the error between target and the actual output of an artificial neural network. So target here refers to your data, your training data and your test data, and actual output here refers to the output of your model. During the training of an artificial neural network using the backpropagation algorithm, the weights and biases are adjusted to produce desired outputs of the artificial neural network. Error is calculated at each iteration and is backpropagated through the layers of the artificial neural network to adapt the weights. So error here is a measure of difference between the output of your artificial neural network model and the desired output. The weights are adapted such that the error is minimized. Once the error has reached a justified minimum value, the training is stopped and the neural network is validated before implemented to solve a given task. Remember, this is a machine learning tool, so you have to do your model evaluation and model validation as usual. So the backpropagation involves two phases: forward pass and backward pass. In forward pass, we will be computing the output, we'll be feeding in the inputs and computing the outputs of the artificial neural network. And in the backward pass is where we adjust or adapt the weights and biases. Before we derive the backpropagation algorithm, we first need to set up an artificial neural network model to be used in the derivation, which is given on the next slide. So this is our artificial neural network model for which we want to derive the backpropagation algorithm to adjust the weights and the biases. So we have to set up first so that our derivation is clear. For example, the number of input neurons is referred to as capital I, and this is input neuron I, where I equals to 1. So this is input neuron 1, input neuron 2. This is hidden neuron 1, hidden neuron 2, hidden neuron 3, because our capital J is 3. The number of output neuron is referred to capital K. So this is output neuron 1. And I've explained what does WHJI mean and WOKJ means. So WO referred to as output neurons, K refers to the output neuron it is connected to, and J is from which hidden neuron it comes from. And similarly, HJI refers to hidden neurons, J refers to the number of or the output a hidden neuron J, I refers to the input neuron I. So for example, if we are talking about the weights between these two neurons, we will call this weight to be WH22. The weight here we would refer to as WH31 and so on. And this is BH1, BH2, BH3, this is BO1. So our neural network model has the following assumptions. Remember, we are interested in deriving the backpropagation algorithm now. So that's why we are making these assumptions so that the derivation would make sense. So we are, in this derivation, we'll be looking at two-layer neural network model and one set of hidden neurons. So we have two layers. This is hidden layer and this is output layer. Neurons in one layer are fully connected to the neurons in the next layer. So as we can see, each neuron is fully connected to the neurons in the next layer. Input neurons have linear activation functions. Hidden and output neurons have logistic activation functions. Assume the firing angle of the logistic activation function C equals to 1. So what is C? If I go back, this is C. So let's assume C equals to 1. Bias weights are used with inputs of 1 for hidden and output neurons. This is always true for all cases. The input to bias weights is always 1. And the number of input, hidden, and output neurons are denoted as I, J, capital J, and capital K respectively, as I've explained. The weight between input neuron 1 and hidden neuron 2 is denoted WH21. Similarly, the weight between hidden neuron 3 and output neuron 1 is denoted as WO1K. The bias connected to hidden neuron 1 is denoted as BH1, and the bias connected to output neuron 1 is denoted as BO1. Given the linear activation function, the output of input neuron 2 is X2. The sum of inputs to a hidden neuron J is denoted as SHJ. The sum of inputs to an output neuron K is denoted as SOK. So where is SHJ? Once again, SHJ is the sum of signal that enters hidden neuron. So if we are talking about hidden neuron 2, the sum of signal is called SH2. The outputs of a hidden neuron J and output of output neuron K are denoted YHJ and YOK. So this is YHJ and this is YOK. That's all for this part. We will continue with the actual derivation in the next part of the module.